Now let's move to our second aim. What was our second aim is to find pressure at any point. How to find, or how many ways are there by which we can find pressure at any point. So suppose the vessel is accelerated along horizontal by acceleration a. So we will be again be moving in the frame of vessel. This is the first point that you should always do. So here is the water column, which is when vessel is at rest, it will suffer a acceleration in the reverse direction a, and the gravity as usual in the downward direction. Consider a point P at a depth y from this inclined surface, and it is away from this surface a length L. Let's remake it. So this was our point. This was our inclined surface. It was away from the inclined surface a length L, and it was below a depth y from this inclined surface. Since this is theta, so this will also be theta. This is also theta. Now at this point we will be writing pressure by three ways, and both these three ways will must give us the same pressure, that we will also be checking whether both three methods yield the same result or not. So first of all, we will be finding pressure here at this point by traveling along this direction. We will be traveling along this direction. So apply the same method, travel along this, or apply Pascal's law. So pressure at this point, suppose this point, the pressure is P. So pressure at this point is P is equals to P naught plus rho gy. Rho gy, because we are traveling in this direction. Now if we will travel in this direction, so here acceleration A exists, here G was existing, here acceleration A exists in this direction, means pressure will be more at this point. So again P is equals to P naught, since this point is exposed to atmosphere again, so P naught here the pressure will be P naught, and from this point we are moving a length L to this point where we have to find the pressure. So P is equals to P naught plus rho AL. So I have written it directly. What you will be doing, you will travel like this in this direction, then you will travel like this in this direction, and write the pressure. So you will be getting this only. This is first way, this is second way. Okay. Now there is another way to write the net pressure, means to write the pressure at this point. What is it? Let us see that also. So this was our surface. Now this was our point, and it was a length L away from the inclined surface and at a depth of y from the inclined surface. Now find net acceleration. What is the net acceleration? So net acceleration for this whole water column, will be perpendicular to the inclined surface, that we all know about it. I have told you that water surface always inclines itself perpendicular to net acceleration. What will be the net acceleration? One acceleration is in this direction, one is in downward direction, so net acceleration will be in this direction, and its value is a square plus g square. I've already told you about the same, and it will be perpendicular to the surface of water. So now this is P. You take a point directly perpendicular to this point, this the pressure where we have to find the pressure. We have to find the pressure at this point. Take a point here just perpendicular to this. Here also the atmospheric pressure exists, but the let us say its length, the distance between P and P naught is x, but this time along this direction, if we will travel, we will be traveling along this direction, finding pressure at this point. We have to consider a square plus g square as our acceleration. Okay. So we will be doing the same and writing the pressure again. So start from this point P naught. We are traveling with the direction of net acceleration, so P naught plus rho root of a square plus g square into this length, we have taken it as x, and finally we have reached to this point P. Okay, so rewriting this, we will be getting P is equals to P naught plus rho a square plus g square to x. So these are three ways. This is second way and this is third way. These three pressure must be equal, but we have to prove that how these pressure are equal. So let's make this triangle again. This was theta, this was y, and this was the point where we have to find the pressure, the point P. It was away from the inclined surface a length L. Now if we can express the second and third pressure in terms of first, that means we have proven all the things, because second and third pressure, if they are equal to first, then obviously we have proved that all the three pressures are equal. Pressure in terms of this, so that we can get rho gy here, we can get rho gy here. So see, we can build one relation that y divided by L from this triangle y divided by L. Let us first try to prove this one. Okay, try to convert this second to this first. So y divided by L in this triangle is tan theta. That means L is actually y divided by tan theta. Okay, now here g is coming, but we are in the expression we are having a. In the second expression we are having a. L we have find in terms of y, so that's no problem, but a we have to find in terms of g. So from earlier conditions we know that a by g is tan theta, so a will be g tan theta, g tan theta. Okay, so these are the two things and we are done. We will be equating these two in this second equation and try to match it with the first. P naught plus P is equals to P naught plus rho, acceleration is g tan theta in terms of g, this L is y upon tan theta. Tan theta will cancel out and we will be getting P naught plus rho g y, which is similar to the first one. So that clearly means that the first and second were equal, both are equal pressures. Now what was our third pressure? It was P is equals to P naught plus rho root of a square plus g square into x. This was x, it was perpendicular direction, this was x. So we have to express this third equation in terms of first. What was our first equation? It was P is equals to P naught plus y, P naught plus rho g y. If we will be getting this rho g y again by doing something, so that means the third pressure is also equal to first one. So let us try to express first of all x in terms of y. How can we do that? We know from this triangle that x upon L is sine theta, and L we have evaluated, L was our y divided by tan theta. So we will be equating this here, and what we will be getting, x is equals to sine theta into y divided by tan theta, that will yield y cos theta. Okay, solve it, you will be getting x is as y cos theta. Now let us put here and try to match rho root of a square plus g square y cos theta. So our expression is not matching yet. We have to remove these two variables, a square plus g square and cos theta, then only we will be able to match it with it. So we know tan theta was a by g. From here, by trigonometric ratios, you can make out that here perpendicular is a, base is g, so hypotenuse will be equal to root of a square plus g square. From here we can find cos theta. We have evaluated hypotenuse. Cos theta will be g divided by root of a square plus g square. Sin theta is, we can also find sin theta. Sin theta will be a divided by root of a square plus g square, but it's of no use. We need to find actually cos theta. Now we will be putting this in place of cos theta. So p is equals to p naught plus rho root of a square plus g square g divided by root of a square plus g square, this is our cos theta, into y. This and this will cancel out and it will give us the same expression as first one. That means third is also equal to second is also equals to first. Means all three pressures are actually equal. So according to the question may ask in any format, so you just have to travel from one point to other to find the pressure. The method I have already discussed in earlier videos, so that will not be that big issue. But you should remember that you can travel along net acceleration direction, you can travel along the gravity, you can travel along the acceleration which is given to the vessel. Means in this direction you can travel in any direction, but you have to take the components accordingly to find the pressure at this point. Okay, so this was just an analogy to show you that all three pressures are equal.